Hello, I'm Debbie Bart. I work at NERSC in the Data Analytics Services Group. And while they're just setting all this up, I'll just mention I really liked Mike's penultimate slide showing the disconnect between researchers and data scientists. I am that interface layer. That is basically my role at NERSC. It's our role in the Data Analytics Services Group. We kind of provide the interface layer between the research scientists and the data scientists and the computer scientists and the hardware. So that's kind of the perspective that I'm coming from. My background is in particle physics and cosmology research, so I sort of have the perspective of a user coming to use the systems that we have and that we support at NERSC. And so this is what I'm going to be talking about is how we are containing HPC for HEP users. Okay, so my thanks to Andrew Putnam yesterday for this rather nice analogy comparing our compute resources. I think of your laptop as being something like a golf cart, easy to use, easy to drive, easy to steer, easy to control. Your average data center, a commodity cluster, is going to be something like a Volvo, I would say, mid-range and very reliable, 100% uptime. Whereas a supercomputer, which are the systems that I work with, this is something more like a supercar. It's very highly engineered, amazing performance, but not necessarily easy to use. And in the data analytics group, a lot of what we do is working with scientists who are accustomed to driving controls that look something like this, and they come to our supercomputer center where they have this amazing power, this amazing performance available, and they're confronted with a user environment that looks something like this. And so what I'm going to be talking about maybe for the next 10 minutes or so is exactly why it's such a complex environment to be working at a supercomputer center. And the kind of advantages and disadvantages of that. And then I'll be talking about how we are working to make supercomputers more easy to use and more performant for your average scientist. And a lot of that is based around container technology. Okay, so this is a chart showing the performance in gigaflops of the top 50 supercomputers in the world. And you'll note that this is a logarithmic scale. And the point that I want to make here is that there's an enormous amount of compute power in the top 1 to 10%. And this is the case in many things in our society. A lot of the power is concentrated in the top few percent. But the difference with supercomputers is this power is accessible to all if only you know how to use it. So these supercomputers, especially the top ranked ones, are really powerful, and there's a reason why they offer a lot of power, and they also have a lot of perhaps issues when you're trying to use them. This is inevitably the first time the technology has been tested at such scale. These are kind of like test beds for new hardware and new software, and so that's system software as well as the software that the scientists are running on these machines, the applications that we're running on these machines. So this means that they're not trivial to use, but there is such an enormous amount of compute power there. I really think it's worth attempting to run your code on these machines. And this is where we are involved in making this easier for you guys. So I want to talk a little bit about what makes a supercomputer a supercomputer, in my opinion. So HPC is high-performance computing. And that's a term that's used to refer to large commodity clusters as well as supercomputers. What I'm really talking about here are supercomputers. And this is a computer that's designed to act as one enormous compute unit rather than a commodity cluster, which is a bank of perhaps thousands, perhaps tens of thousands of weakly connected compute cores. And the real difference, I think, is encapsulated in these pictures. This is a couple of pictures I took from our machine room a few months ago. This is the back of one of our commodity clusters, Mendel, showing the interconnect there. And this is the back of one of our supercomputer cabinets, Cori. As you can see, it really is all about connection. There's orders of magnitude more cabling involved in supercomputing than in your traditional commodity cluster. And I can really emphasize this by telling you that when Cori was installed last summer, it took about a day for the engineers to get the cabinets in. There's something like 64 cabinets came in, and they were all wheeled in the day, connected to the floor, all powered up pretty quickly. It then took over a week to do all the cabling, to do all the networking, to get this custom interconnect up and running. And there's a reason why we have this very complex and very specialized interconnect. It's so that the compute nodes can communicate with each other with very little latency at very high speed, so that you can run a massively parallel application that requires these compute nodes to all talk to each other very efficiently. And that's a really powerful resource as the scale of the computing, the problems that we face is really growing year on year. And this isn't a new thing. This kind of level of connection isn't a new thing in supercomputing. I was here in Seattle a few months ago for another conference, and the conference night out was the nerdiest thing I've ever done. We went to the Living Computer Museum here in Seattle. Has anyone else been there? Oh, you should go. It's really fun, especially if you're a kind of a hardware nerd, like I am. It's a really fascinating place. So they have vintage computers that have been lovingly restored by experts to be functional. And one of the things that they were showcasing for us was this Cray 2 supercomputer that they just purchased. And so the thing that I was really impressed by this, to start with, it has 2 gigaflops of compute and maybe 2 gigabytes of memory. I think everyone in this room has a phone that's more powerful than this supercomputer today. But even back then, in the second generation of the real supercomputers, the entirety of this cabinet is filled with this kind of level of cabling. And it's an amazing amount of cabling and connections required even back then to get the kind of performance out of the hardware. Okay, so that was the old-fashioned supercomputers. This is the computers that we have at NERSC that I'm going to be talking mostly about today. So we have 2 supercomputers on the floor. We have Cori. It's a Cray XC40, the number 6 fastest supercomputer in the world. And we have Edison, which is a Cray XC30, down at number 72. There's a couple of things that I want to point out about this. Cori is an interesting system. We have a mixture of 2 different types of compute nodes. We have Intel Xeon compute nodes and Xeon Phi KNL nodes, Knights Landing nodes. So we have a heterogeneous compute environment here. But having so many 68-core Xeon Phi KNL nodes means that we have a really excellent performance. We get up to something like 14 petaflops running in sustained mode and a theoretical peak of around 28 petaflops. Now, the thing that I want to point out here that I think is really impressive, I think it's really interesting, Edison's about 3 years older than Cori. But Cori is about 10 times more powerful than Edison in terms of the compute power. So it's almost an exact correlation, a 10-time factor. Edison's about 10 times less powerful in compute terms than Cori. But it draws the same amount of electricity, it draws the same amount of power. In just 3 years, the computing technology has gotten to the point where we can have a machine that's 10 times more powerful, but yet draws the same amount of energy. And that's where we've seen this discussed earlier this week in a couple of different talks, the interaction between Moore's law and Denard's law. I think this is a really nice illustration of that the technology is focusing on giving us more compute power for less electricity costs, because we simply couldn't afford to run a machine that had 10 times the power costs. Okay, so we're not just a compute shop. We're not just providing scientists with CPU hours. We also have massive file systems. And these massive file systems that have to be engineered quite carefully to keep up with the amount of compute that our users demand of us. So we have something like 10 petabytes of GPFS. We have nearly 40 petabytes of a Lustre scratch file system. And nearly 30 petabytes of that is on Cori alone. So Cori has nearly 30 petabytes of scratch space. And we also have about 2 petabytes of flash storage, which is our burst buffer system, which sits inside the high-speed network in Cori. And this is a layer that's designed to give high-performing I/O for those apps that really need the kind of performance you can get from SSDs. So what do we do with all these supercomputers? Well, NERSC, in case you're not aware, is really the workhorse for the Department of Energy Office of Science. So we have something like 7,000 users on our system. Perhaps 3,000 of those are active users, but we have about 7,000 people with NERSC accounts. And these are scientists from 700-odd projects across all the different offices of science from the DOE. So we have people running genomics reconstructions codes. We have people running large-scale climate simulations, material science simulations, fusion energy simulations and data analysis, and of course particle physics and cosmology, both the simulation side and the data analysis side. So we have an enormous amount of different users that all have different demands on our systems. And what we'd really like to be able to present them with is a system that just works, that they just bring their code to the supercomputers, and this fabulously advanced technology just works like magic for them. Of course, the reality is a little different. There's a tremendous amount of sort of lever pushing and button pressing and frantic work going on in the background by a large team of engineers, trying to make sure that these systems actually work well for the users. And of course, a lot of this spills out into the user experience. They just have a show of hands. How many people have actually run directly on a supercomputer? And how, right, keep your hands up. Take your hand down if it was easy. There's a handful of people who found that easy. That's good to see. Yeah, it's not necessarily trivial to run your code on a supercomputer. They are amazing. They have fantastic capabilities, but they're very highly optimized for a fairly specific purpose, and that purpose is running massively parallel applications at large scale. So they have this screamingly fast interconnect and amazing network capabilities, a very specific custom compute environment, a custom operating system, and optimized system libraries that allows you access to this power. Another feature that supercomputers typically have is no local disk. This is something that can break quite a lot of your standard data analysis pipelines. So there's two issues here that I'm going to be coming back to again and again, the issue of portability and the issue of scalability. So portability just means that you can't run very often the same code on your laptop and just port it directly to Cori and expect it to run out of the box. And if it does run, then I can almost guarantee you that it's not going to run well. Scalability is a big issue. The optimizations we have to allow tens of petabytes of storage system to be available to hundreds of thousands of compute cores simultaneously means that we don't deal very well with metadata-intensive compute loads. And that's a lot of what our data analysis users are bringing us, is metadata-intensive compute nodes. So I'm going to now talk a little bit about containerization and how we're using containers to solve these kinds of problems. We've had a nice introduction to containers in the previous talk, so I don't need to go into that too deeply, but I want to talk a bit about the implications of portability in particular. So this is a nice image from the CERN computing site. It shows all the places where data is going around the world from CERN. And this is something that I think is true in all areas of science. As a scientist, I'm going to run my code wherever I can get the cycles. I'm greedy for compute time. I can always handle more compute time, and I'm going to want to run my code wherever I can. And if I'm going to run my code in multiple places, and I'm going to want to make sure that I get the same answer at multiple sites. And so portability is a really big point. And your code has to be not just portable, but reproducible. And we just heard quite a lot about the issue of reproducibility or perhaps reusability. But one thing I want to emphasize in that concept is the importance of the computing environment. That if you're running your code somewhere that has very specific system libraries, then you're potentially going to get a different answer. If you're running your code in a place that has different floating point precision rules, you're likely to get a very different answer to your, in your results. And that is something that you really have to be aware of when you're considering how you're going to deal with containerizing your code. And so I'm going to be touching on how we're using containers for portability, reproducibility, but also for scalability, how we can take advantage of some of the features of containers in order to be able to scale up our code easily and seamlessly from a laptop to a supercomputer. So I don't need to go through what a container is, but I'll talk a little bit about some of the downsides to Docker, which is the most popular and kind of the industry leader in containering. So Docker pretty much brings out our sysadmins in hives. They don't like Docker for a number of reasons. Perhaps the most important is the security question. If you're running in a Docker container or in a Docker image, you have root access to that image. And if you have root access to that image, then there's always some possibility you could break out of your container and have root privileges in our very expensive and very delicate super machine. So that's no good. Also, if we have to mount in our file systems into this image, and if you have root privileges within the image and we give you access to our file systems to your data, then you're going to have root access to our file systems, and that's also unacceptable. And there's also some performance issues. If you run a straight Docker container on something like a supercomputer, then you're just not going to have access to the system-specific and system-optimized libraries. And so this is something that, and in particular, Docker has no MPI capabilities. And if you're running on a big supercomputer, then really you're neglecting a lot of the advantages of running on a supercomputer if you're not running on parallel. So there's two HPC groups which have developed effective solutions to this. Both of them happen to be from Berkeley Lab, Singularity and Shifter. And I'm going to be talking through some examples of how we've used Singularity and Shifter in HEP, in particular, to solve some of the problems inherent in running on HPC. So the Singularity and Shifter are very similar. They both fix the security holes. They have full integration with system software and architectures. And they're both designed to enable apps to scale up seamlessly on HPC systems and on supercomputers. Perhaps the main difference between Singularity and Shifter is that Singularity creates their own custom image files, where Shifter imports and uses image files either from Docker or some other format. And the other difference is sort of the philosophy of how these tools were developed. So Shifter was developed very much with a supercomputing sort of mindset in mind. So it's a more centralized control model. The admin controls the images and the deployment of those images. Whereas for Singularity, it's more of a user control system. But they both work well, and they both work well on commodity HPC clusters as well as supercomputers. So to make a couple of quick examples of how Singularity in particular is being used to aid code portability. Elise jobs are being run within Singularity containers at GSI. It's executed via the workload manager, Slurm. So this is another aspect of containers, is that of Singularity and Shifter, is that they provide integration with system resource managers and workload managers. University of Cape Town is deploying Jupyter Hub using Singularity. So in this case, the Jupyter Hub kernels are deployed in Singularity containers, which allows the jobs to run within the container while maintaining access to the local node resources. Now, this example is one of my favorites. It's a sort of extreme example of code reproducibility. Back in around 2002 at Berkeley Lab, there was a postdoc who got funding to write a data analysis suite for an earth sciences lab. It's basically analyzing field data from geology research. And this was running on this postdoc's desktop computer. At some points, the funding ran out for the postdoc, and as is so often the case, this code was just never updated. There was never money or time available to update the code and have it run on a more sophisticated architecture. So this one desktop machine was running for about 13 years in this lab, doing the same data analysis, chugging away, until the lab security, cybersecurity team noticed it and made them take it offline. That was in 2015. And so for a year or so, the group just didn't know what to do. They didn't have the funding, and now they didn't have the resources to do their data analysis, to rewrite this code, to update the code. And so they turned to Singularity. And so Singularity was able to take an image of the hard drive of this ancient machine and port it to a modern operating system. And now the code is running, and analysis is continuing in this extremely old-fashioned code base, but something that works, and something that works for the scientists. So now I'm going to give some examples talking about using containers for scalability. So Python is kind of famously not scalable. Python import statement is very metadata intensive. Python relies typically on shared libraries. And if you're trying to do many Python interpreters, many processes all doing the same import statements at the same time, you just get into metadata hell with the increasing number of processes trying to access these shared libraries. So you can use containers to to avoid this problem, because if you have Python installed on your container, then the metadata operations are moved to the compute node rather than relying on your central file system metadata servers. So this is an example showing how Singularity helps Python scale up on NFS. This is on NFS, and this is a log scale here of the time required to do some import statements. And you can see if you just have this straightforward Python installation, scales terribly. Singularity really helps, something like an order of magnitude faster to be running this in a container. We have a similar example for Shifter running at NERSC. This is the Pynamic benchmark. It's a Python benchmark that just does a lot of imports. It imports a lot of different modules and tries to start up processes here on 4,800 different processes. You see, if you try to run this on our Lustre Scratch system on Cori, you're looking at something like 12 minutes just to get this started up. And that's something that's unacceptable on the kind of scale of compute resources that we're trying to offer. Shifter reduces this to something like a minute. So by using containers, you're really reducing the overhead in running Python at scale. And a nice example of this happening in a production environment is from this project called Toast, which is doing CMB simulations at large scale. So these are simulations that are running on the whole machine of Cori. And they used Shifter to distribute the Python wrap code to all 9,600 odd nodes of Cori. And this just wouldn't be possible without wrapping the Python libraries within the container. And another nice point that I want to make here of Shifter in particular is that you can mash in the system libraries, the optimized system libraries. It allows codes to run efficiently at large scale. So they compiled their image with a standard mpitch library. And then as Shifter imported this image, it was able to remove that layer of the image and mash back in a system-optimized version of mpitch, which gave them really excellent performance running on the high-speed network. So the last example I'm going to give is work that's done by Mustafa, who's here in the audience today, using Shifter to create a Cray local disk, and again avoid some of the problems inherent in doing metadata-heavy workloads on our big distributed file systems. So this is using the Shifter per node cache feature, which is a way of creating an XFS file system on our Lustre file system, but have it loop-back mounted into the image. And so it's loop-mounted into the compute node. And this means that you're moving the metadata operations to the compute node rather than having to go through the file system metadata server every time. And this reduced the amount of time required to cache the 30,000 odd queries to the conditions database, reduced the time from 30 minutes to a few seconds. And your only overhead is copying this conditions database in the first place. And that takes something like a minute. And again, this is something that's in production. This is a way of enabling this production workload to run on our systems at scale. And it's actually running right now. It's been running very successfully for the last week or so. Okay, in my last 0 minutes, I'm going to skip over my slides talking about data science at scale, because I just want to point out that a lot of what we're doing in the data and analytics group at NERSC is not just using containers to get codes running well and get our scientists' workloads running well on the computers, but also embracing new ways of doing this. So we're working a lot with experts at Intel and developers at Julia to have high-performance languages and high productivity languages running well at scale. I already talked a bit about Python. I want to talk about just mention a project that we had recently that I think is really neat, that is a demonstration of variational inference on 8 billion parameters. I'm obviously not going to go through all this in any detail, but I'll point out that this was the first Julia application to exceed a petaflop performance. I think it's probably the first Julia application to exceed a teraflop in performance, frankly. This is a really impressive effort, a collaboration between computer scientists, Julia developers, and domain scientists to make a demonstration of the value of Bayesian inference and the computational feasibility of variational inference. So this was able to process the entire SDSS data set of 178 terabytes of image data in 15 minutes. This is a really nice achievement, and it's really pushed Julia into a whole other level of performance. And this is part of an effort that's underway right now we've just launched a big data center at NERSC where we're partnering with developers, co-developers, industry experts, and academics to work on these kinds of problems. And there's been a couple of talks that mention this already this week, and I think you can expect to see exciting things coming from this collaboration in the next year or two. So I'll stop there, but I'll invite you to surprise yourself by how easy it could be to run on a supercomputer today. Thanks.
Nice talk. I was wondering, do you know why the singularity people didn't use, rewrote their container image format? I mean, they didn't. I'm not pushing for Docker, and don't like very much what they're trying to do with containers, but there are actually two standards for containers images. The usual story about standards.
Yeah.
So why didn't...
Yeah, I'll repeat the question. So the question is why Singularity developers chose to develop their own image formats. I don't know the answer to that. I think there are some advantages in how you can optimize that image format for HPC systems, whereas we chose to sort of mangle an image that gets imported to make it run well on the NERSC systems. When I say we, NERSC developed Shifter, and so I know more about how Shifter was designed. But in Singularity, I think they have more flexibility by deciding on their own image format. But you can still use Docker images in that. You can import a Docker image into the Singularity image format and run that way.
Because the two standards, ACI and OCI, I mean, presumably the ACI one, which is run by the Rocket people, is a bit more performance-oriented than the Docker one.
Yeah, so there are image standards that are more performant than Docker, perhaps, but Docker is the one that most people are familiar with, and it's the one that grad students are most excited about working with. So.
And then I just one question: do you need people who want to work with this Julia or any other language really to test payloads on supercomputers, like, I don't know, Go, for example?
I sense someone has a project here. The question was whether we need people who have projects in these more productivity-oriented languages, like Go, for example, to run on machines. Yeah, the Celeste project was really driven by a realization that Julia is starting to be a really popular language, and it just didn't have the performance. It's designed to be naturally parallelized language. It doesn't have the performance at scale, and so by having this science project, it's a genuine science project. This isn't just a sort of stunt run. We're able to really get somewhere with Julia. And yeah, if there are similar challenges available in using Go, then I think we'd definitely be interested in developing that.
At the beginning, you talked about the fancy and expensive communications networks like Cori and other supercomputers. With the applications in these containers, how many of them really need that network? In your car example, a Volvo carries 4 or 5 people, and a supercar, 1 uncomfortably.
Okay, so the question here is how many apps really need the high-speed network? So, I mean, one interpretation of this question is how many codes actually need to run in parallel at all. If you have any code that's running in parallel, even if it's fairly loosely parallelized using MPI and multiple nodes, it's going to perform much better if you have a well-optimized interconnect. But if you have just single core jobs running, single thread jobs running, then the interconnect is not really going to help you with that. Oh, how many apps? Oh, I see. So how many apps really need it? Well, it depends on whether you define the number, how you define the workload. We have this kind of conversation all the time at NERSC. There are codes that take up the majority of our compute hours, and those are all massively parallel big simulation codes. And then there are codes that take up the majority of our job slots. And those tend to be smaller scale, a few compute nodes, but we have many more of those kinds of jobs run, just in terms of number, than the large sort of full machine scale ones. So it depends on how you define the numbers, but I'd say 90%. Yeah. Oh, I see. So which of these applications needed it? So Celeste needs this kind of, anything that's running at the kind of scale where you're on more than a handful of compute nodes needs this interconnect to not lose all your compute time in message passing latency. So this project, yep. Yes, the TOAST, the CMB simulation did, for sure. Yeah. So I'd say 50% of the work that I showed in these slides really needs the interconnect.